attending so many events. You were in that event, right?
Yeah. I'm somewhere in, I'm covered by Severio's arm.
Sorry.
What was that?
That was like International Women's Day, wasn't it? Yeah. That was actually my first ever event at GDG Cloud. It was a lot of fun, loads of people, and actually from there I met Amanda and Sav, and also Eddie, who's in the back, who's always helping record super high quality videos and content. But yeah, it's a great community. If you're free, come along to one of the events, and I guarantee you won't be disappointed. So, yeah.
And then we also have another event which has been going on, which is the Women Tech Makers JavaScript. So basically, we are teaching about 60 folks how to code, getting started in JavaScript. So it's been really cool. And there is a third one that Jesus was there. Maybe he could say a few words.
Well, I heard about the event and show up just pretending to trying to learn something new, and what overwhelmed me was the enormous quality of the people that were there, and the great community that they have formed, and in which I'm involved now. And I try to come as many events as possible, because I have a really amazing time with them, and it's one of the best parts of being in London for me.
Oh, thank you. Thank you.
So yeah, as Amanda was pointing, we've launched this new series of events under the Women Tech Maker umbrella, trying to either refresh or helping people getting started with JavaScript. I want to also thank particularly Chiara, which is running away. She's very shy. So one of the things that I want to try and do before the end of the year is having Chiara overcome this. Chiara, can you come here, please? So she's super helpful, but she's a little bit shy of the spotlight. I think that she deserves the recognition for all the effort that she's...
I don't know what to say.
So,
yeah, she's the one who's sending all the emails and working so hard, so thank you, Chiara.
Yes. Okay, I think that one last thing before we get started tonight. At the end of the event, we are going to give away a few licenses for JetBrains products.
Before we talk about that, we
yes.
just have a slide here.
Okay, we have...
That these Google developer groups, they don't exist just here in London. They're like everywhere in the world. There's like almost 900. So here are some of the events that we collaborated with some other chapters which are in the UK, but also in Japan you have GDGs too as well, right? And in San Francisco there's GDGs everywhere. So maybe if you're traveling somewhere around the world, just check on meetup.com or maybe other websites like Eventbrite if there's something going on. As you were saying?
Yeah, as I was saying, we've got, this is our account. You may know it already probably, or not, but it's that one. So if you tweet something tonight, pictures, shout out, something you like, questions, whatever, at the end of the event, we will sort with the Wheel of Fortune.
Wheel of names?
Wheel of names.
So basically, if you do a tweet, if you're on Twitter, you just add the @GDG Cloud, and then in the end, we're going to give away 3 JetBrains licenses away. So tweet away.
So.
And?
Yes.
Last slide.
Feedback. So on feedback, we have some extra swag sorting and extraction. So after you have watched the events, the talks tonight, probably after you have also had some snack, food, whatever, let us know about anything from the quality of talks, how much you don't like us, or how good or how bad the food is.
And
so
if you don't like us, tell us how we can improve.
Absolutely.
We really want to hear from you.
Any criticism, as long as constructive, it's very welcome. And we have prizes for that. So get in touch.
So the first speaker tonight, Kaz, could you join us here, please?
So yeah, Kaz is a staff developer advocate from Google Japan. And tonight is going to talk to us about AutoML tables and BigQuery. So we're getting set up. So did you get wet? I see a few people with umbrellas, some with...
Who here is a first-timer? Nice.
Quite a few. we hope that you are going to stick around.
His slides are up.
So we are going to remove ourselves and go speed.
Okay, thank you so much. And thank you so much for inviting me to such a wonderful community here. And also thank you so much for taking your time for my session, BigQuery, ML, and automated tables. Is there any, my self-introduction. What is that? What is that? Oh, okay. Anywhere? Okay.
Thank you.
No problem. So I'm Kaz. I have been working at Google Tokyo office for over 8 years, almost 9 years. And for the last 4 years, I have been working as a developer advocate, which is like an evangelist for developers. So I usually traveling around the many countries and attending many meetups and events and talks about the technologies from Google, especially focusing on machine learning and the big data analysis like BigQuery and TensorFlow and Cloud AI. And today I'd like to talk about two products, BigQuery machine learning and AutoML tables. So let's talk about the BigQuery ML. How many people have used BigQuery? Oh, like almost 50%. Thank you so much. So, and how many people has heard about BigQuery? Anyone who heard about BigQuery? Okay, like 50%. So BigQuery is a data warehouse from Google Cloud's the platform. So if you have like terabytes of data or tens of terabytes or maybe less than that, even for the tens of gigabytes or hundreds of gigabytes, rather than using the MySQL database, online transaction database for the data analytics, it's much faster and cheaper to use the data warehouse, such as BigQuery, or from AWS, they have the Redshift as a data warehouse service. So usually, many people are splitting the log data, storing the log data on the BigQuery or the data warehouse services, so that that makes you easier. That makes it easier to make analysis on the log data or any data you have collected on the data warehouse. And the reason why BigQuery can provide a super fast performance and cheaper the price compared with the other competitor the product is that the BigQuery is a massively power processing query, MPP, so-called MPP. So for every single SQL you would be running on BigQuery, that will be processed with 2,000 CPU cores every time, and running the hundreds of the SSDs and hard disk drives simultaneously. So that massive power is the reason why BigQuery can provide the massive power of the data analytics. At the same time, it can provide the you can use that at the 1/3 of the cost of the other competitor services. So it's super fast, yet it's so inexpensive. That's the reason why many AWS users are starting to use BigQuery only for the data analytics. So actually in Japan, I think the majority of the BigQuery users are AWS users. They're using the AWS EC2 or S3 for the building the infrastructure, but they know that the best solution for their AWS users is for data analytics is using the BigQuery. So this is one of our killer products from GCP. So data warehouse, the concept has invented in around the 1990s. There has been many data warehouse products for the on-premise devices or enterprise systems. And in early 2000, there was a concept of the business intelligence created. The products such as the Tableau or the QlikView, many of those business intelligence, the products allows you to dig into the data and easily visualize those data and get some insights. And at around 2010, I think I remember that was 2010 at Google I/O. Google has announced the first BigQuery as the commercial product. And at that time, I wasn't an employee of Google. Not yet, yeah, because it was like 9 years ago. So I was so surprised to see the demonstration of the BigQuery in 2010 at Google I/O, because they have run a query on like 1 terabyte or maybe tens of terabytes within 20 seconds or 30 seconds. It was blazingly fast. So that was the first time Google have started providing the BigQuery as a service. And now the latest technology we provided is the BigQuery ML. We have integrated machine learning into the BigQuery directly. So I'll be talking about that. Because the BigQuery, the machine learning is very hard to deploy or harder to introduce. At first, you have to understand what is machine learning. How many people have used machine learning, by the way? Not so many, like under 20%. Thank you so much. So you have to learn the machine learning by reading the books, textbooks, or hiring the data scientist. And maybe there will be some ways, different ways to use machine learning. The popular way is to use the Excel or Google spreadsheet to import the data from the BigQuery or any other the storages like a Google Cloud Storage or MySQL or Oracle or anything. Anyway, you cannot run the machine learning algorithms directly on the data warehouse or database because it's too big. You always have to extract or sampling some of data to the Excel spreadsheet or some runtimes on of the TensorFlow or scikit-learn, those the machine learning tool set. So every data analytics textbooks you would read or you would run, most of them are talking about how you can extract the data from the data warehouse or database and do the sampling and run the machine learning algorithms on a smaller runtime, such as Excel spreadsheet or the TensorFlow or scikit-learn runtime. So that's the biggest challenge we have been seeing for the machine learning data analytics. So BigQuery solves this problem. We have integrated the machine learning directly into the data warehouse or database inside it. So you don't have to extract any data from it. You can run the machine learning inside data warehouse. And you don't have to move the data from BigQuery. And also, you can do the iteration of the data analytics inside BigQuery by using SQL. So you don't have to write the many Python code, tens of the or hundreds of lines of Python code for the data analytics. All you have to write is the SQL with some new syntax for the machine learning, the training and prediction. And also another challenge you would see when you are trying to use the machine learning is the many complex data scientist tasks, such as the hyperparameter tuning or pre-processing and everything. Those the complex, tedious tasks are written in the machine learning textbook, but we are trying to automate a major part of the machine learning tasks in the BQML, BigQuery ML. And also we have integrated the machine learning feature into the original BigQuery UI. So you don't have to use two different user interfaces. Usually the data analysis or the data scientists have to use the many different user interface. At first you have to use the BigQuery user interface to extract data, and then you have to use the TensorFlow, TensorBoard UI, or the scikit-learn UI, or Jupyter Notebooks for the data analytics. But we have integrated everything into single user interface. And all you have to do with the BQML, BigQuery ML, is to write a few lines of the SQL, and that's it. So that you can train a model or use the machine learning model inside SQL. But behind the scenes, we have automated many different things. For example, because the BigQuery is a massively power processing, as I mentioned, you can also utilize the power of MPP for the machine learning, the model training, and also prediction. I'll be showing the actual demonstrations where you can apply the machine learning prediction or the recognition for the image data, 1 million image data in tens of seconds. I'll be showing the demonstration later. And also the learning rate. Learning rate is one of the different hyperparameters where the data scientist would be struggling with trying out the different learning rate. But we automated to find the best learning rate for the machine learning algorithms. Or splitting the data. You have to split the training data into training data set, the validation data set, and testing data set. That's one of the popular tasks for the data scientists, but we have automated that as well. All the data cleansings, many data scientists are struggling with the data cleansing and data preparation, pre-processing. Like if you have the null values in some certain columns, how you can pre-process those null values, replacing that with the 0 or some medium values or something like that. That is also automated. Or standardization. If you have many different scales in different columns, you have to standardize before applying them into the machine learning algorithms, or one-hot encodings and class inversing. Those are all the typical the tasks you have to do, and you can learn them on the machine learning textbook, but majority of them are automated with BigQuery ML. And BigQuery ML supports many different popular machine learning algorithms, including the logistic regression, which is the most popular and simple tool for the classification, or DNN classifier. DNN stands for the Deep Neural Network. So if you want to get the power of the latest deep learning technologies, you can use it as well. Or linear regression, or K-means clustering, or max factorization. Max factorization is a basic calculation you are using for the collaborative filtering, the recommendation systems. Or you can even use the TensorFlow model running inside the BigQuery. Let's take a look at the actual demonstration. So this is the user interface of BigQuery. If you are already using the BigQuery, then you should be familiar with this user interface. And if you want to use the machine learning within the BigQuery, all you have to do is to write some SQL like this. This is a SQL to train a new model with SQL. In this case, we are using some sample table to create to train a new model with the logistic regression algorithm. And these are all the pre-processings you would apply against this sample table. By the way, in this case, we are using the Google Analytics session data as a sample data. And to try to use the machine learning model for predicting whether this user should be buying your product or not. This is a typical use case of the machine learning against the Google Analytics data. So specifying that Google Analytics data table and do some pre-processing on each columns and train your model with logistic regression. And you press this button, then you have to wait for like tens of seconds. Usually it wouldn't take tens of minutes. Usually most of the training would finish within tens of seconds, or less than 1 minute. And then you can use this trained model with the prediction SQL, where you can specify the trained model, name of the trained model. Let me run it. So now the BigQuery is running the prediction against the Google Analytics sample table, and we got the prediction result. So based on the model prediction, it looks like there will be the purchases by the users in the United States for about 200, or Taiwan and Canada and Japan. So these are all the predicted results from the machine learning models. And in the past, if you do the same things with BigQuery and the other tools, you have to extract some data from BigQuery and use the Excel or the Jupyter notebooks running the TensorFlow or scikit-learn, and train the model within the Jupyter notebook, and send back the model to the BigQuery. So that was so tedious to do all the iterations in the past. But as you can see, now everything is super easy. Write 2 SQLs for the training and prediction, and do everything within BigQuery. So that's the basic feature you would get with BigQML. So because this is a machine learning, this could be applied to many different use cases, including the marketing or retailing, or retail services, or IoT, or gaming, where anybody want to find any spam users for the IoT or financial, or anybody who want to predict any the revenue focused on the retail. So the applications could be empowered by the BigQuery machine learning. And there has been already the large enterprises who has been trying out the beta version of the BigQML already, including the Sony and Qubit and Smart Parking and Mercari. And as I mentioned, the BI is one of the important part of the data analytics. So usually many people are using BigQuery with the BI tools such as Tableau or Looker. And BigQML is already integrated with the Looker. As you know, the Looker has been merged with the Google recently. And so you can utilize the power of the BigQML from the Looker also. So you can get started with the visualized data for exploring the data with BigQML Looker. And then you can create the model inside the Looker by using the user interface and get the report for the trained machine learning model and check the result within the Looker user interface. So even for the business users or salespeople or marketing researchers could utilize the power of the BigQML by using those BI tools because they are integrated. And there are some new updates for the BigQML. BigQML itself is now provided as GA, and now having some other new features such as the k-means clustering as better or matrix factorization as alpha. K-means is one of the most popular algorithms for the unsupervised learning or clustering. So if you have a bunch of the users, for example, if you have a bunch of users for your services, by using k-means, you can easily make a clusters, like a cluster for the user who tends to like this particular features, or a cluster of another cluster of the users who tends to like another feature. So if you want to make some clusters of the users, this feature will be useful for you. Max factorization is, as I mentioned, this is the basic calculations required for the collaborative filtering for build your own the recommendation system or deep neural network of using TensorFlow. In the past, there was not easy to integrate the TensorFlow with BigQuery. But now the TensorFlow is supported on the BigQML officially, so it's much easier to have the integration. So for example, data scientists train their design and train their TensorFlow model, then integrate use the TensorFlow model inside the BigQML. I will show the actual demonstrations later. Yeah, again, so you can import the TensorFlow model for the prediction in the SQL. So what would be happening if you integrate the BigQML with the TensorFlow model? So one example could be the image similarity search. This is a demonstration called the Queried Smart, where we are using the BigQuery for the image search. Usually, you cannot use the image data or any unstructured data inside the data warehouse, because usually in the past the data warehouse only supports the structured data. So for structured data, it's powerful, but for the unstructured data such as the image or audio or natural languages, the data warehouse didn't provide much the functionality or the performance. But by integrating the TensorFlow with the BigQuery ML, you can easily implement the things like this. For example, if you choose one of those key images, like this B image, now I'm executing a SQL that searches for the similar images against these key images, against 1 million images stored on the BigQuery in real time. Usually this query would finish within 30 seconds. So yeah, now it took like 79.9 seconds. So as you can see, so you can easily find these similar images to these key images. This was not looking for the B images. Usually people are putting the many labels or tags to the images for storing in the database, but you don't have to do that with BigQML or TensorFlow, because TensorFlow model is a deep learning model that can recognize the patterns or colors or shapes or those patterns in the images. So it can directly compare the image patterns or features directly with the two different images. So you don't have to put any tags on those images. But you can easily get the list of the similar images in like 20 seconds or 30 seconds against 1 million images. If you want to do these things with the usual vision API or image recognition API, you have to make like 1 million calls or at least 100,000 calls against the APIs. Or you have to run the TensorFlow batch processing against the 1 million images. But because BigQuery is a massively parallel processing, you can do the massively parallel predictions against the data within BigQuery. And this is just one example where you apply the technologies to the image data. But you can apply the same technologies to any kind of the data you have in a data warehouse, like audio data or NLP, or any business that you would have. For example, if you have any the financial transactions stored on the Oracle or MySQL, you can use the BigQuery to find who are the users who could be doing any fraudulent or fraud use cases. By using the deep learning technologies for finding the patterns for those fraudulent use cases or user activities, or finding the spam users, or for IoT devices, this could be applied to find any malfunctioning the sensors or any machineries in your factories. So finding the similar images is just one example you can use. Yeah, I'd like to show how this demonstration was implemented. So in these demonstrations, it was comparing the similarity between the images. And to do so, we have used the two SQLs. For the first SQL, we have applied the deep learning model called MobileNet version 2. MobileNet is the one with the popular image recognition model. Usually people are using MobileNet for getting a label such as cat or the dog or the flowers. But instead, we are getting the feature vectors. Feature vectors means a bunch of the numbers that represents the shapes or colors or patterns in the images. That represents the feature of each images. Then you can store the feature vectors for each images and compare, get the distance between two feature vectors. So if you have a feature vector for a single image and another vector for another image, you can use this very simple calculations to calculate the distance between two images. So you can instantly get the similarity between two images. And you can apply this to the 1 million images easily. So that was the BigQuery machine learning. Any questions you have? So, hi.
So once the models are created, is there a way of actually backing them up or exporting them?
Yes. You can export the model to outside the BigQuery, to the Google Cloud Storage or any other format. I think you can save the model.
Is there a way of exporting so that explainability?
What's that?
Explainability?
Explainability, yeah.
So there are tools which do explainability, like line framework, or is it proprietary model data format?
Yeah, actually, the BigQuery itself doesn't provide any explainability feature at this time. But yeah, because the model is exportable, so you can apply exported model to any open source explainability tool, such as maybe Sharp, SAG. Yeah. Okay. Any other questions? Okay. So that was the first product I wanted to talk about, and the second product is AutoML tables. BigQuery ML is designed for the users who understand the basic of the machine learnings. So that's the reason why I mentioned about many different algorithms, such as the k-means or the max factorization. But AutoML tables is much easier. This is designed for the non-machine learning users. So with the Cloud AutoML, actually there are many different the products which has the Cloud AutoML names on it. So we have Cloud AutoML Vision or Cloud AutoML Video, Natural Language, and Translation. But all the products is trying to automate the process of the machine learning development. So in the past, it's not so easy to develop a machine learning-based systems. You have to hire data scientists or data machine learning engineers and let them design and build a machine learning model and integrate it with any infrastructure with the DevOps team. So it costs so much time and cost. But we are trying to lower the bar for introducing the machine learning in productions. So that's the target of the AutoML. So all you have to do is upload your own training data to Google Cloud Storage and press the training button and wait for 1 day or maybe half a day, and you get the result as a report of the accuracies. And once you have finished the trainings, all the infrastructures are deployed as a REST API, so you don't have to build your own infrastructure for the machine learning models. And now the latest the product is called AutoML tables, which is optimized for the structured data. So these days, many people are talking about the AIs for the unstructured data applications, such as the image recognition or the audio speech recognition or the natural language processing. But actually, many enterprises or companies are using the structured data for the majority of the cases. For example, if you have the tables like this in your MySQL table, and you would have the many tasks or the problems to predict what would be the best pricing for the product items. So in the many enterprises, they have that kind of problems for the structured data. So also in the past data deep learning problems are targeted for the images or the videos, those unstructured data. The demand or requirement from the enterprises are mostly based on the time series data or structured data. So we really wanted to solve that problems for the retail or finance or marketing or transportation, healthcare, without hiring expensive data scientists, who would cost like I don't know, $300,000 per year, things like that, or like that. So it's so expensive to hire the data analysis or the machine learning engineers nowadays. So if you can automate the majority of the machine learning development process, then you can apply many different verticals and industrials can introduce the power of the machine learning for every single the problem solving. So that's the reason why we have introduced the AutoML tables. That is optimized for the structured data. And to build the machine learning systems, as I mentioned, it's not an easy task. You have to collect your data, and you have to define the schema, and you have to analyze your data, training data, and training, and evaluate the performance of your model, like accuracy, and deploy your model to the infrastructure. These are all automated by the AutoML tables. So you don't have to do that by yourself. You have to do some the UI clicks on the user interface. For example, if you are importing some data from data warehouse like BigQuery to the machine learning environment, you always have to do something called the feature engineering. The raw data could not be used for the training as is. Always you have to do some data collection or cleansing or some padding any missing fields, anything like that. Also, you have to determine the schemas or data types. Is it numbers or is it timestamp? Is it some categories or lists, things like that. And also, you have to be aware of the imbalanced data. For example, if you want to predict a certain types of the users, you have to collect the many training data for certain types of the users for like tens of thousands of the records. So you have to think about the imbalancing or missing values or outliers. So after that, you have cleaned up all the data, and with the AutoML tables, we are trying to automate the majority of those tasks for the data scientists. And also another important task for the data scientist or data engineer is to find the best machine learning algorithm or model, whether it should be a linear model or deep learning model, or combining the linear model and the deep learning model, or gradient boosted decision tree, or GBDT. This is a very popular model used in the Kaggle competitions, or the ensembling, everything. So at Google, we have been developing many different, tens of different algorithms for machine learning. And usually you have to hire some cutting edge data scientists to find the best one, but you don't have to do that because we have automated the model selection. So by clicking the training button of the automated tables, it automates everything I have mentioned, like the finding the best model for your particular data set and problem, or how to ensembling, combining the result of the different models, and how to deploy your model to the scalable infrastructure. So let me show some example. So what would be the performance you would get with those automated machine learning environment? This is the one example competitions we have applied the automated text, the tables. There was a competition called Mercari Price Suggestion Challenge in the Kaggle competition, and where they have a table that has the many production descriptions. By the way, Mercari is the one of the most popular selling application in Japan. It's like eBay in Japan. So many people are using Mercari for selling the second-hand products. But the problem is defining the best pricing for selling each second-hand goods. So they wanted to build some AI systems to predict the best, to suggest the best pricing. So based on the product information such as the name or condition or category or descriptions, they had competitions to have all the data scientists training a model, best model, to predict the best pricing for each product. So this is the result we got from all the 1,500 teams who joined the competition. These are all human data scientists, the team with the human data scientists. So this is an error rate of the algorithms. So the lowest is the best. So this is the top data scientist team. They won the award for this competition. And this is the worst the team. And we have applied the automated tables. What kind of performance it can provide for the competition? The automated tables, if you run the training for the 12 hours, you cannot get the best performance with AutoML. But as you can see, it's not so bad. So it's within the top 500 teams. So it's as same as the performance you would get from the senior data scientists. Definitely not the beginner machine learning users. So by clicking just the training button, it's just like hiring a new senior data scientist. And the cost is about $300 for 12-hour training, rather than spending hundreds of thousands of dollars per year for hiring those people. And it's scalable, so you can press the training button any times if you want to train every different models. So you can save the money for training a model or prediction, and also another time and cost-consuming part is the deploying the model on the scalable cluster. Everything is automated. But this is not the best the tool for every use cases. So you have to be aware that this is just an automation for the majority of the machine learning development, not the whole part. So you have to make sure that before applying the automated tables that you have collected the good, high-quality training data. If your training data quality is not great, maybe automated tables cannot provide you a good result. And you have to wait for like some hours, at least 1 hour, up to 24 hours. And yeah, sometimes you cannot get the enough amount of the training data. Automated tables provides the best performance if you have the more than 100,000 records for a table. If it's less than that, like 10,000 rows, 10,000 records, or 50,000 records, maybe the automated tables cannot give you the best result. I can show some the user interface, how you can use the automated tables on the user interface. This is the user interface where it provides the easy user interface for importing your data from the BigQuery or Google Cloud Storage, or you can upload your data from your computer from local file. And then it can automatically tries to detect the data type for each column, whether it's a numeric value or categorical value or timestamp or string and blah, blah, blah. And you can specify the target columns, the columns you want to predict. In this case, this is a data for predicting the bankruptcy of the workers or loaners. So based on the features or columns such as the age or job or marital status, or education level, or the housing status or things like that. The problem is requires to predict whether the loaner would have a bankruptcy in certain time period or not. And also, as I mentioned, if you are using machine learning, it's very important to look at what kind of the training data you will be using for training the data. So the automated tables user interface provides the easy user interface for looking at the statistics or the profile of your training data, like the basic statistics such as the mean and standard deviations, or how many the missing values, or what's the cardinality or distinct values in each columns. So you can easily look at the check whether your training data is clean enough, the good enough for the training. And then you can press the training button and wait for 12 hours. Then you would get the evaluation result from the service. So you can get the usual ROC curve like this. This is the typical matrix you would get for when you train the machine learning models. And also confusion matrix, whether the accuracy you would get for certain labels, whether this person would have a bankruptcy in the future or not. And also, it's very easy to find what are the important columns or features to get the certain prediction result. So in this case, it looks like to predict the bankruptcy status in the future, the duration of the loan could be most important the features where the machine learning algorithm is looking at. And by choosing the prediction user interface, you can export the data to the BigQuery for the batch prediction, or you can easily prepare for the scalable online prediction, the API infrastructure. So you don't have to build your own the GK cluster or the GC instance to run the machine learning predictions at scalable use cases. Okay, see? So lastly, I'd like to show how our customers are getting the benefits from the automated tables. By looking at the cases of the GNP Seguros, GNP Seguros is one of the most traditional, popular insurance company in South America. They have over 100 years of the history in car, healthcare, life, and home insurance. And let me skip this. They have applied the automated tables, whether it works for those use cases like car claim risk analysis or detection of the fraudulent claims in the healthcare insurance and gender labeling. For example, the car claim risk. In this case, they haven't exposed any actual numbers of the performance, but they mentioned that it's really much better performance they are getting from any existing models. And even if you get the 1% or maybe 2% of the increase of the accuracy, the business benefit you could get is huge, because they are spending like over $500 million per year for the car claim payment. So in this kind of the large-scale enterprise use cases or businesses, it's very important to increase the 1%, 2% accuracies for the risk analysis. And also the healthcare fraudulent detection, they were able to increase the 20% of the 30% effectivity compared with their existing traditional in-house algorithms they were using. And again, the result could provide them a huge benefit for them because they are spending over $680 million per year for the payment for the healthcare insurance claims. And in the enterprises, there are many user data which lacks any certain attributes such as the gender or the many different labels. And GNP used the AutoML tables to fill in the gap, fill the gender, put the gender labels for those users. And they were able to get the 99.2% accuracy for detecting whether this user must be a male or female or the other sex. Okay, so this was just an evaluation case. So they haven't introduced the AutoML tables to the production yet, but apparently they will be able to get the huge business benefit. And again, this is not done by the professional data scientists. You can use the AutoML tables even without any machine learning expertise. So that this is the power of the AutoML tables. We have automated the majority of the machine learning, the training tasks and the prediction tasks, so that everyone, even without the machine learning experts, can get the benefits of the machine learning to their businesses. And lastly, I'd like to compare the two different products. So BigQML, the product I have introduced to you first, that was designed for the data engineer who knows the basics of the machine learning and who knows the difference of the algorithms such as the linear models or logistic regression and deep learning models, and who can write the SQL and do their own ad hoc data analytics on that. Whereas the AutoML tables, this is designed for the non-machine learning users, like usual the web developers or usual developers or programmers, who doesn't have much time to learn machine learning from scratch, but who has the training data. Training data is required in any cases. With AutoML tables, you can just press the training button and wait for like 12 hours to get the best result you could get. And we also provide some other options. For example, at the cloud AI platforms, we provide the AI platform product that is used for the running your own Jupyter Notebook on the Google Cloud, or the running your own virtual machines for the TensorFlow. So if you are the cutting-edge data scientist, you can use the AI platform and notebook running on the GCP. If you have the machine learning, the basic knowledge, maybe BigQML could be the best platform. And if you don't have any knowledge, maybe AutoML is the best way to getting started to introduce the machine learning. Okay, that's it. Thank you so much.
Thank you.
Questions?
Questions?
Anyone has a question? Question. You're good. Oh, one here and one there.
I got a question about. Hello. Got a question about your AutoML. When you showed the features generated, you mentioned that it auto-generates the features. Is it able to show you the details of what the features it auto-generated and why?
Yeah, actually, that is the request I was making to the product manager. At this time, we don't provide any detailed report against the auto-generated features because they change. They are trying out many different synthesizing way of synthesizing the new features. So at this time, unfortunately, we cannot provide. But we are asking the product teams.
Okay, but the auto features, I just want to understand, does it do sliding windows and like how much they paid over 3 months?
Yeah.
Okay.
Apparently, it detects how to handle the timestamp the data. Yeah.
Do you think BigQuery would be sufficiently mature now to be used by someone to compete in Kaggle? like to pick up a problem. If I was to pick up a problem from Kaggle, would it offer me enough tools to actually compete?
So question
Kaggle.
Can you use the automated tables for competing in Kaggle? Is it the question? Yeah, you can do that. And actually, the new most of the new competitions in Kaggle has some rules when you are using the AutoML technologies. Usually they have a rules to classify those the different applications, human applications and AutoML applications. So usually they don't allow the AutoML the results to get the hours for that, but you can use that. So it's depending on the competitions, and you can check out the rules on each competitions, whether you can use the AutoML or not.
All right, thanks.
Okay.
Any other last question? Yes.
Yeah, I have one about, once we have the model, in which way you can export this? Because at some point, right, how do you export the model? Export.
The AutoML tables?
Well, no, the model itself. When you prepare, you find a great model or the AutoML found a model. How I can export to making productions? Which is the format or how?
Yeah, unfortunately, AutoML tables doesn't support any export feature of the model. Yeah, so you have to use the prediction API of the AutoML tables to use the model. And the AutoML Vision, there's a product called AutoML Vision that provides the custom model for the image recognition. That allows you to download and export the model to the edge devices like a TensorFlow, right? But that is the only product that allows to export the model. All the other AutoML the products right now doesn't allow you to export the model at this time.
I want to say is, the TensorFlow you just demonstrated for us. Could you also would you be able to show, for example, if I wanted to apply to another application, so for example, like CAD or Blender software, like the drawing to come to life, can I be able to use TensorFlow with attachment behind the programming with Blender or AutoCAD to see in interaction with the 3D model?
So the question is how you can integrate the TensorFlow with the 3D tools such as the Blender? I think that's a tough question, and I don't know how to do that right now. But because usually TensorFlow...
The reason why I say that is because two of us in the front, because we wanted to know is because we are working along with robotics. So in order to have software and implementing with the idea of it was to first use a software that has already used AI. And if we use TensorFlow, for example, it will be able to help us because we don't want to spend too much expensive money, like for example, motors or bipolar motors or LED light. So we want to use the design so it comes to real life. So when we do training, we want to see whether it can move forward and backwards. So once we've done the drawing on 3D, we can then implement it on the electronics. And once we implement on the electronic and audio, it comes to life, and therefore we don't have to propagate the information. It's already been trained, and then once it's all set, when we start building the whole hardware and show it to people, it will learn from an experiment itself instead of going back to another connection on the computer. That way it's self-learning with AI instead of using radar and machine learning and other stuff.
Yeah, I think maybe one way is to use the reinforcement learning. Have you heard of the name reinforcement learning, RL? That is the one algorithm of the different algorithms you can use the TensorFlow. And many people are applying the RL, reinforcement learning, for controlling the robotics devices to find what would be the best move for each motors or the devices to do the certain task, like you catch some objects, things like that. And another interesting things, because you mentioned about the Blender, if you are looking for any solutions for the 3D models, recently TensorFlow model added a new feature called TensorFlow Graphics that allows you to handle the 3D data, model data inside TensorFlow. So that you can combine both RL with the 3D graphics to build your solutions, I hope. Thank you.
Thank you.
Thank you.
Thank you.
Sato-san, thank you very much for coming here again. It's great to have you here 2 years in a row. It's always a pleasure to have you around here.
Thank you so much for inviting me.
And last year there were 2 meetups going on at the same time, so it was a bit noisy. So this year I think we made it up for you. Now we invite Emma.
Yes, yes. So Emma is a developer advocate for Google. I think that when we met her for the first time, she was in Tokyo, but now she moved to Seattle.
Yes,
Yeah.
I did.
So you may have read about her on journals, magazine, websites, because early this
Ooh,
year,
she's famous.
she broke with her team, she broke the record for digits of pi calculated, over 31.4 trillion, if I'm not wrong.
Is that right?
She's going to go in depth about that. So she's going to explain us how she was. This was, I think, this was part of her dream ever since she was a child, and during her working life.
Yeah, you're basically telling everything I'm
Oh, sorry.
So remember to tweet if you want to apply it for the raffle for the 3 licenses in the end, and then in the end we're going to have more snacks and pizzas. For now, we leave you with Emma.
Yes.
Thank you. I think I'm gonna leave the hoodie there. This is a Discord hoodie, if you know Discord. This has some Japanese text, and I think that's really cool. Anyway, thank you. Thank you for having me here today. My name is Emma Haruka Iwao, or Iwao Haruka in Japanese. I'm a developer advocate as Kaz, and I work for Google. And that's my Twitter handle, just in case you need it. Oh, and actually, I went to Milton Keynes yesterday, and went to the National Museum of Computing, and I saw one of the rotating machines that the Alan Turing team used to break the German cryptography. So it was really cool. If you haven't been there, I strongly recommend you visiting the museum. Anyway, so as got introduced, this is the news that came out this March about Pi. And I'm going to talk about it. But before actually talking about the details of the calculation, I'd like to talk about some of the history of Pi and computing, because we have a lot to do. This is from the Art of Computer Programming, a computer science textbook. And Donald Knuth says human progress in calculation has traditionally been measured by the number of decimal digits of pi. So we as humanity collectively have been calculating pi for literally thousands of years. And by the way, he recently updated, revised the textbook, and he put my name on that. That's really cool. And so this is just a small summary of the history. But in BC 2000, ancient Babylonians seemed to know that pi was close to 3.1. So that's the first decimal digit, decimal place. And then in the 15th century, a mathematician in India, Madhava of Sangamagurama, he said he did 10 digits. So that's only 9 digits improvement in more than 3,000 years. And in 1949, one of the first electronic computers, ENIAC, was used to crunch pi up to 2,000 digits. And since we got computers, the improvement, the speed, got much, much faster. And in 1973, we got 1 million digits. And in 2009, we got 2.5 trillion digits. And all of these records were made by some of the biggest computers, like supercomputers. But in the same year, Ballard, he is the author of FFmpeg and QM. He did 2.6 trillion digits on his personal computer. And suddenly people realized, okay, we have fast enough, desktop computers. Did I say supercomputer? Desktop computer. And suddenly people realized that, okay, we can do something like this with just a regular computer, not like supercomputers. And people started computing again. And in 2016, this is the previous world record with 22 trillion digits. And this year, we did 31 trillion digits. Why is it so difficult to calculate pi? Of course, with pen and paper, it's obviously difficult. But with computers, it involves a lot of data. For 31 trillion digits, we need about 170 terabytes of storage. And regular computers don't have memory of that amount, right? Usually you have 10 terabytes or 20 terabytes. That's the maximum you have. And so you need to use disk or some kind of storage. And disks are slow than processors. And the speed hasn't really improved in the last 20, 30 years. For example, in the 1990s, regular hard drives had sustained throughput of about 40 megabytes per second. And processors were running at 100 megahertz, for example. And today, we have processors running at 4 gigahertz, or sometimes 5 gigahertz, while the throughput of regular hard drives got only to 200 megabytes. So that's like, processors got thousands of times faster, and disks got only like 4 or 5 times faster. That's the difference over the last 30 years. So we are hitting the memory wall. Especially for Pi, the space complexity, the storage requirement is O n log n squared to the power 2, but the time complexity is O n log cubed to the third power. So as you get more digits, the storage requirement, the memory requirement, gets really, really big. And this is a screenshot of the task manager running a Pi calculation. And the CPU usage is just 13%, while the storage is used at the maximum throughput. So that's the difficult part. And why don't we just use supercomputers? Well, you can. And in fact, since 1954, we've used supercomputers to calculate pi. It's a little bit tricky to define the first earliest supercomputer, but NRC is considered as one of these, and it was used to do 3,000 digits, and they spent 30 minutes. And all of the 1 million, 1 billion, 1 trillion, these milestones were hit by supercomputers. So they are fast and great. And not only the number of digits, but also the duration of these calculations got improved. Because in 1954, they couldn't run a program for more than like 20 minutes. The computers were not reliable, and they would break down while you are running a program. While in 2002, they managed to run this program for more than 400 hours. So that's the improvement, not only in performance, but also in reliability. But at the same time, it is very, very difficult to write a program for supercomputers today. This picture is currently the world's fastest supercomputer, Summit. It has more than 2 million GPU cores. This is not the GPU like execution pipeline. This is the actual GPU chips. More than 2 million GPU cores across 4,600 nodes. And it's difficult to write a program that scales well across 2 million cores, right? So yes, it's theoretically possible, but nobody has tried yet. So we decided to use cloud. The exact number of digits is 31 trillion, 415 billion, etc. So this is the first 14 digits of pi. And I thought that number was cool, so I chose that number. And we spent 121 days, so that's even longer than some of the previous world records. And we used a program called YCruncher. This is something you can download from the internet. This is developed by a software engineer, Alexander Yi. He doesn't work for Google. I just downloaded his program and run it. Yeah, really. You can just download the program and run it, as I did. And the main compute node has 96 vCPUs and 1.4 terabytes RAM. So there's nothing special. It has a little bit more memory than your laptop. But yeah, it's just a regular computer. And one of the interesting metrics we had is the total I/O over 4 months. It's 9 petabytes for reads and 8 petabytes for writes. If you work on big data, a petabyte doesn't really sound like a big data, right? You sometimes deal with like hundreds of petabytes of data. Maybe you don't, but some people do. But for a single program, like producing a lot of data, this is still a large number, and you can't afford to have like even a single bit flip. If you have a single bit failure anywhere during the calculation, the entire result will be wrong. So you need to make sure that every bit in this I/O and during the calculation is correct. And if you don't work for Google and somehow decided to do the calculation, you'd have to pay approximately $200,000 or 160,000 pounds as of today. So it's still kind of expensive. I wouldn't pay this amount of money, but it's expensive. But there are a couple of different cost-saving measures that we could have done, but we didn't. And with all of these measures, the total cost would have been like $60,000. This is still a lot of money. That's more than my salary. So it is expensive, but it's certainly cheaper than buying a supercomputer. Let's see. Why would you want to use cloud? As I said, you can just download a program and then run it instead of writing everything from scratch. And not only the software, but hardware. You can just start a new cluster like in a minute with cloud. Building a supercomputer is actually harder than you might think. It takes multiple years. The POSK project of Japan, that the name is Fugaku. They are literally working for more than 10 years to design processors and build a cluster. So it takes multiple years to build a supercomputer. On the other hand, for cloud, it just takes a minute. And cloud machines are often more reliable than desktop computers or laptops. They have server-grade hardware, and all the cooling and power supplies are redundant, so it's often more reliable than your home power supply. And even if something goes wrong, all you need to do is to restart the virtual machine, right? You don't have to go to the hardware store and buy a new component. You just need to restart the virtual machine. So the mean time to recover is much shorter. And also from the operation standpoint, cloud is oftentimes easier to operate. For example, in order to take backups, you just need to take snapshots of the disks instead of copying everything from one hard drive to another. And you can literally operate everything remotely. For example, I moved from Tokyo to Seattle while running the calculation, but I didn't have to move computers from Japan to the US. While I was packing everything, the servers just kept running the calculation. This is a little bit more technical detail of the overall cluster. So we had one machine that's the biggest machine in green in the picture, and running Windows Server OS. I picked Windows Server because YCruncher is a little bit more optimized for Windows rather than Linux. And I'm not very familiar with Windows Server, but I have some experience with Windows Desktop, so I chose that. And in order to provide 240 terabytes for storage, I prepared additional storage servers pictured in blue here. These are regular Linux servers. And I talk the reason why we have so many servers like soon. For the main compute node, it's rather simple. In order to make the calculation faster, you need to have more cores, more computing like power, processing power. And in order to reduce the I/O, you need more memory. So biggest machine is the best choice. And last year, when I did the calculation, there are two options. One is the N1 Megaman 96 machine type with 96 vCPUs. This is a two-socket Skylake system with 1.4 terabytes of RAM. And the other option is N1 Ultraman 160 with 160 vCPUs on a 4-socket Broadwell system. And this has almost 4 terabytes of RAM. And it seems like the second option is a faster machine, and it could be for some workloads. But I picked the first choice because it has the newer generation of the Intel CPU. It's Skylake and newer than Broadwell. And because it supports AVX 512 that could compensate the fewer number of cores. And it has only 2 sockets. And Y cruncher is not really optimized, or it's extremely hard to run this kind of calculation on many sockets. So I chose that one. Just in case you're wondering, if you have multiple sockets in one machine on Intel architecture, you have memory modules attached to each of the processors. And if you're accessing remote memory, you need to go through the other CPU and access the memory. So it's actually slower. And as you have more sockets, for example, with one socket, you have everything local, 100% local. But with 2 sockets, you have 50% remote. And with 4 sockets, you have 75% remote. So the memory access could be actually much slower if you have more sockets. So I stick to the 2-socket system. And for the storage, on Google Cloud currently, you can't mount more than 64 terabytes of storage to one node. 64 terabytes is usually a good number, but for this particular calculation, we needed 200 terabytes. So we had to work around this limitation. And we decided to use ISPAGI, that's the network block storage protocol. And everything happening on top of the operating system is not subject to the limit. So this worked really well. And we also decided to use SSDs, not hard drives, like regular standard persistent disks. Because nobody had used SSDs before. And also, some people still think that SSDs are not durable enough to handle petabytes of writes. But they are now. So I wanted to prove that. And in order to combine these different drives, you need to use RAID. And Windows has software RAID, and Y cruncher has its own RAID layer. And Y cruncher's RAID is more optimized for that particular workload, so I decided to use that. And also, when you take snapshots or backups, if you have one single giant drive, you need to take care of the synchronization between different drives. You have only one file system and one metadata, and if you take backups of inconsistent state, your backup might be incomplete. But if you have separate drives, you have metadata for each of the drives, so you don't have to worry about the synchronization issues. And I run the benchmark with different number of nodes, 20, 26, and 32. These are guesstimates. And 24 seem to perform the best with 26 gigabps for reads and 16 gigabps for writes. And the network throughput limit for egress bandwidth was 16 gigabps at that time. So it was performing pretty well. By the way, if you have a Windows server, and have more than 26 drives, you don't have enough drive letters, right? There are only 26 letters. If you use like Chinese or Japanese, there are more characters, so you could mount more than 26. But so you need to mount these disks into directories like on Linux. If you repeat the same calculation today, we have much better infrastructure. So if you use cloud, you will benefit from these improvements that we continue to make. This is not only for Google, but all the cloud vendors work on these infrastructures. We have twice as fast network with 32 Gbps egress bandwidth, and we have two additional machine types. One is the computer optimized VM with 60V CPU running at 3.8 GHz, and the other option is the memory optimized virtual machine with 416V CPUs with 12 terabytes of RAM. So these are much bigger, and you could use one of these. If you use these options, you could probably finish the calculation in half the time. So instead of spending 4 months, you could run actually in 2 months. So that's really cool. But we didn't have that last year. One of the challenges we face during calculation is live migration. So live migration is there to help you keep your infrastructure up and running. When we perform maintenance in the VMM or host OS, we live migrate guest operating systems into another node so that we don't have to stop virtual machines when we perform maintenance. Or when there is early signs of hardware failure, for example, increasing number of ECC errors or some kind of early signs, we live migrate virtual machines to a more healthier node and prevent hardware failures. And usually live migrations finish in 10 milliseconds or 50 milliseconds, so it's usually very fast and you wouldn't notice there was a live migration. But this was not the case for Y Cruncher. Because in order to live migrate a virtual machine, you need to copy all the memory into other machine. But if the workload is very memory intensive and continues to write to memory, you can't keep up with that pace. And for example, a typical memory bandwidth for a two-socket machine is about 200 gigabytes per second. So that's 1600 gigabps. And we don't have that fast network yet. The network bandwidth is usually 100 gigabps or 200 gigabps, depending on how you configure your machines. And Y Cruncher, in fact, rewrites the entire 1.4 terabytes of RAM in less than 15 seconds. So you need to eventually stop the virtual machine and copy something. And this graph is a histogram of the memory bandwidth for Y Cruncher on a single socket Xeon machine. The average bandwidth is actually more than 50 gigabytes per second. So that's still faster than a typical network. So migration blackout, so first live migration happens this way. So you try to copy everything before actually stopping the program. And then you stop the program and copy the essential memory region. And then restart the program and try to copy the rest. So you need to have a blackout period that everything freezes and VMM works hardly, works diligently to copy the rest of the memory regions. And it usually takes no post copy. So 97% of the live migrations do not involve post copy at all. And 98.5 percentile of post copies. So 97% doesn't involve post copies at all, and the 50 percentile. So that's 98.5 percentile free while the post copy wait time is just 91 milliseconds. So that's how fast a live migration is. But for Y Cruncher, this post copy was 15 minutes, not 15 seconds. It was 15 minutes. And the default network timeout value was too short for that purpose, especially the default timeout value for Windows iSCSI was like 6 seconds or something. So I had to edit the Windows registry values to change the timeout value. And after setting the value to 900 seconds, everything was working fine. And if you have a long running process, you probably need backups just in case. And Y-Cruncher automatically saves checkpoints during the calculation. So checkpoints are internal states of the calculation, and you can restart the calculation in case the program stops. And so you need to copy these checkpoint files into another storage, and we use persistent disk snapshots. These are regular disk snapshots on Google Cloud, and you can just copy everything. And I wrote a script to make the backup process. It's just a single command or a few commands, but every time you take backups, you don't want to type everything. So I created a shell script and I run it manually once or twice a week, because Y-Cruncher deletes the old checkpoints before writing something new. So you need to make sure that there is actually a checkpoint file. And if you haven't restored from a backup recently, that means probably you don't have a backup. There are a lot of examples when people thought they had backups, but they couldn't restore from these files. So I practiced some disaster scenarios, like I intentionally stopped the program, or like shut down the operating system, or shut down one of the storage servers, and made sure that I could actually restore from these backups. And it saved my life twice. And monitoring, you don't want to stare at the screen all the time for 4 months. So I set up both Stackdriver and Datadog for monitoring. Stackdriver is Google's monitoring tool. It's a first-party tool. And we have Datadog. This is a third-party tool, and I kind of wanted to learn about both of these, so I set up both. And this is the dashboard we actually used. We have the progress number, so it's 37% down, and uptime of all hosts combined. And we have the CPU usage and networks bandwidth. So you can actually see the status of the cluster here very, very easily. And I also shared this dashboard to my managers, so they could check how I was working on the situation. Like, I didn't have to report every single time, every single week. And when the progress value was approaching to 100%, my managers were like, how's the calculation doing? And they asked me quite often, and I was like, yeah, it's very close to the end. So we had some real conversation based on this dashboard. And also, we set up a few alerts. The first kind of alert is for individual host downs. So if something goes wrong with a particular virtual machine, you will get an email saying, hey, this virtual machine is down. And the other alert is the average CPU usage of the main compute node. And if that's less than 1%, you get an email. And because we are running the program for 4 months, I didn't have to set the window to, for example, 5 minutes, 5 seconds, or 1 minute, because as you see, the CPU usage changes really, really wildly. Like sometimes it's less than 1%, and sometimes it's 80% or 100%. So you can't actually set a specific value there. So you need to actually wait a little bit and make sure that the program has actually stopped. And this 1 hour window worked really well. And there was only basically me checking the status of the cluster. And if I was sleeping or flying or something, I couldn't check the status. So I didn't have any problem with that 1 hour window. And after four months, you get this screen. This is the actual screen. You see some statistics and start time September 22nd and the end time January 21st of 2019. So that's 121 days. So what we learned. So in hindsight, as I said, this seems like a simple task of downloading a program from the internet and running it on a cloud platform. But before we actually began or finished the calculation, nobody actually believed that you could crunch a world record-breaking Pi on cloud, or you could run a single virtual machine performance with network drive attached with heavy I/O. Now we know it's possible, and everyone can repeat the same configuration with that. And I think that's the cool aspect of using cloud. You can just get some new ideas from other people's architecture and repeat that in your environment and work on your own problem. And the second part of the talk is how I got here, or in other words, why would you want to calculate pi in the first place? I was kind of obsessed with the number pi since I was a kid. I was born and raised in Osaka, Japan. Osaka is the third biggest city in Japan after Tokyo and Yokohama. And we have a strong accent, actually. It doesn't sound as good as like the British English accent, but we still have an accent. I started programming when I was 11 years old. Some of my first programming languages were C, Pascal, and x86 assembly. So I was writing small tools and games for MS-DOS, that's pre-Windows. And this is the actual program I wrote in 1997 to calculate pi. And this only used a double type to hold the numbers. So that's only capable of doing like 16 to 20 digits. And the world record in 1997 was 60 billion digits. So that's the difference of me and a world record holder. And I wasn't good at math. So I just copied this source code from a textbook or something. So I didn't understand any of these at all. And even my high school teacher came to me and said, hey, your math grades suck. You should, no, he didn't say that, but he spoke in Japanese, of course. But yeah, your math grades are not great. So why don't you study liberal arts instead of like science? So I did. But I kind of liked programming. Sometimes you may wonder, what's the best way to learn something? What's the best way to learn JavaScript or React or Angular? But I just kept writing. Like, this is actual source code, again, from my high school age. This is the awful code. For example, you have magic numbers there, like 2 or 393. Like, these are like something you wouldn't want in your source code. And there's no comment at all. And the function name is put-waku. So it's a combination of the English word put and waku. Waku is a Japanese word for a border. So I should have named the function as like draw border or something, but I couldn't come up with a name. So that's my English skill. I got a little bit better than that time. Anyway, so I kept learning programming, but in school I studied like liberal arts, and then in university I started studying education and psychology for the first year. And my professor came to me and said, hey, you seem to like computers. Why are you here? Like, do you really want to study education? And I was like, yeah, maybe I like computers more than education. I was honest. So he suggested I switch majors, and I joined the computer science department from the second year, and I finished my master's. I still think this change was one of my best life decisions so far. Not necessarily because you need to study computer science to become a professional software engineer, but because this is a change from what I was told to do to something I really wanted to do. And I still appreciate my step here. And then I started working at Panasonic. Panasonic is a Japanese manufacturing company. And I was working on embedded systems like car navigation systems or factory automation. So that's very different from web applications. And I quit the job 2 years later and joined a company called Free. This is a mobile game company in Japan, and they are running web services. So I began working on the infrastructure. So I was kind of doing something like site reliability engineering, like taking care of servers. And I applied for Google and didn't get an offer, got rejected like 4 times before actually joining Google. So the important lesson here is you can apply for the same company multiple times. Really. And after 5 years, I joined Google and as a customer solutions engineer, and then moved to cloud as a developer. Okay. And I moved from Tokyo to Seattle. Just in case you don't know, Tokyo is on the left side and Seattle is on the right side. Both of the cities happen to have a tower. And if you don't know where they are, Tokyo is on the right-hand side and Seattle is on the left-hand side. We use a world map in a different kind of shape. So we have the Pacific in the middle of the map and Atlantic on the edge in Japan. And in other places, you have this kind of world map. I always wanted to work in another country. Like I had spent my entire life in Japan. I was like getting tired of it. So I tried, and this change was a really interesting change. I'm a Japanese citizen. That means I don't have to worry about a visa in Japan. I can change a job. But in the US, I'm an alien worker, technically. Alien. So if I lose my employment, lose my job, I have to leave the country. There is no option, like plan B. And I can't change my job while I'm on the visa. So that helped me learn about different life situations of different people. So sometimes people cannot afford to change a job. And I speak Japanese much, much better than English, in fact. And English is my second language. As you saw, I have improved a little bit, but I still sometimes struggle with English communications in the US. But there are good things, like same-sex marriage is not legal in Japan, but in the US it is legal. So my partner and I got married, and the wage gap between men and women in Japan is 25%, while in the US it's 18%. And 18% is no way a good number, but I feel the difference, unfortunately, every single day when I work in the US. But as an Asian woman, the US is a little bit tricky to work in. So we are well represented. These numbers are the workforce representation at Google in technical roles. And we have 45% Asian workers in the US. So this is a US only number, but we have 45% in the US. Asian workers, and 51% white workers. And the Asian population in the US is just about 6%. So we have way more Asian workers. However, if you take a look at the career progression rates across different race and gender, we struggle to get promoted. So as you have a green bar there, that means you have more senior executive level people. And if you have a red bar there, that means there are more junior people. And the leftmost bar is for white men, obviously. And the rightmost bar is for Asian women. So we have lower career progression rates even than, for example, black women or Hispanic women or black men, etc. So we are somewhat represented in the workforce, but we are often marginalized, unfortunately. Sometimes being a minority or underrepresented person gives a nice little boost. For example, I had some extra news coverage based on my race. Like the first article says, by Japanese engineer, and the second article says, it's queer Google dev. So they are based on my traits, not like the work, by my ethnicity or like queer status. But usually it works against. So I didn't have a Wikipedia article, and somebody decided to create one. And then somebody jumped in and said, hey, this person doesn't worth a Wikipedia article. We should delete it. And they started writing comments like, this is a trivial achievement, or there's nothing novel or creative. She just downloaded the program and run it. Or, yeah, this MR is marginally notable. We shouldn't have a Wikipedia article. And I knew I wasn't alone because this happened before. So this person didn't have a Wikipedia article, but she won the Nobel Prize. And so somebody created an article for her. And then a group of people jumped in and said, hey, she just won a single prize. She doesn't deserve a Wikipedia article. And but if a Nobel Prize doesn't deserve worth a Wikipedia article, what kind of achievement would you need, right? All the male winners in that age had, in that year had no Wikipedia articles, and just she didn't, and even some people opposed having that. So now I can say I had the same experience as a Nobel Prize winner. So that's kind of cool. And we have a kind of awkward track record in terms of gender. So this is ENIAC, the electronic computer built in 1944 or 45. And these two women standing in front of the machine are some of the earliest software engineers in the world. These are women because people thought hardware engineering was the cool thing and software engineering was something boring. So they let women work on software engineering and men worked on hardware engineering. And they only had men at the launch party and didn't invite these women. But without these people's work, of course, we wouldn't have the machine working. So they did equally amazing work, but that's a fact. But we have a lot of great figures in the history of computer science. This is Grace Hopper, who worked on a team to develop COBOL. COBOL is an ancient programming language that nobody really likes today, but without COBOL, we wouldn't have the same society as we do today. So that's an important milestone. And this is one of my favorite computer scientists overall, Margaret Hamilton, who worked for NASA and wrote software for the Apollo space rocket. And the pile of papers she's standing next to is the source code she wrote for the project. So that's how much they worked to deliver the space rocket to the moon. And when you think of great achievements in history, we tend to think of people actually in the picture, right? When we think about the Apollo project, we think of astronauts standing on the moon, but there are actually thousands of people working behind the scenes and working equally hard. So I think it's important to recognize these people's work. And this is one of the recent examples. Dr. Katie Bowman, who led a team to develop software to decode a black hole image from radio waves. And this black hole happens to exist very, very far from the Earth, about 400,000 light years away from the Earth. So the radio wave signals are very, very weak, so they had to write some special algorithm that I don't really understand, but she did a great job there. So we have a lot of people, but so there are people who work really hard and leave a great achievement, but we just don't have great representation. So I had never thought I would become a professional software engineer really until my first job. My high school teacher told me that software engineering is a hard job and you probably wouldn't be able to do that. And also, I never thought I was a good software engineer because I failed the job interviews many times, or maybe I'm good in the classroom, but not really a good software engineer in a professional workplace. And even after breaking the world record, so after the program finished, I went to my manager and said, hey, manager, I think I have broken the world record. Do you think I should write an article on my personal blog, or do you think Google might be interested in writing something about it? So And he was like, yeah, we can go bigger. Like, let's reach out to the PR team. So that's my self-assessment of myself. That's how small I estimate myself. And everybody probably has a similar feeling when you have difficulty in your life. That's something called impostor syndrome, and everybody at some point suffer from that. And that's healthy, and we just need to know that we are actually good enough for what we are doing. This is the end of the talk. But in a summary, the combination of existing tools like cloud or something you can download from the internet really helps sometimes solve a new problem. And a corporate culture and teamwork really matter. So during the project, my managers didn't really care how much I spent. No, they really supported me doing a project. And cloud is a new tool for large-scale computing. In the past, we used supercomputers to do this kind of work. Now we use cloud, and cloud is even better in some ways. Like you can create a new architecture, new design, very, very quickly, without paying a lot of money. Because you can, after you shutting down these machines, you don't have to pay for that. And I didn't have a supercomputer. I still don't have a supercomputer, unfortunately. But with cloud, my childhood dream came true. That's my talk. Thank you very much.
Questions?
Hi, I was just wondering, because you said you were in Japan for your whole life and then you moved to Seattle. Did you notice any particular work cultural differences that were notable?
Because Google has a somewhat similar culture in different offices. I didn't really, so I was surprised that in Seattle, we get Amazon package delivered on the next day. I was expecting something slower. That's the biggest culture shock I experienced in a good way. In terms of work culture, people come to the office very early in the morning, like 8 or 8:30 in the morning. In Japan, usually people, especially software engineers, come to the office around 10 or 10:30 to avoid the rush hour. But in Seattle, people come earlier and leave earlier. So that's sometimes they leave around 3, and instead they come earlier, and they continue to work at home, like after having dinner with family or something. So I think that's some of the biggest differences. Oh, the Seattle office is much quieter. So what we call the atmosphere or culture, the Seattle freeze. So people, well, no, I'm not talking about a particular people or group of people, but if we have some surveys saying people in Seattle don't want to make new friends. Like 50% of people said, no, I don't need any more new friends. So that's kind of the culture we have. But people are very friendly. Did I answer the question? More or less. Yeah, thank you.
Is this data available for download somewhere?
Yes, so we published snapshot images of the results disks, and you can just copy these snapshots and create a disk on Google Cloud, because it takes many hours to download the results. They are probably 15 terabytes, and it takes a little while to download all of that.
Oh, it's not compressed.
It's compressed. So
compressed already. Oh.
So pi is a random sequence of numbers, and you cannot compress something random. So they are just packed. If that's a regular text file, that's exactly 31.4 terabytes. So we have a packed file, but they are still big. So the way to download the files is available on the internet. If you search like Google Cloud Pi, there is a Google blog post, and in the blog post there is a section of instructions to download or use these snapshots. And also, I actually published these files on a web server. So if you really want to copy these files, I can send a link. But they are big.
Just going to say, well done. Congratulations, Emma.
Thank you.
I suppose my question would be, what's your next record that you're going to break?
That's a good one. I don't have a good answer. So certainly you can try something bigger with the improved infrastructure, but that's a linear progression, and I'd like to have exponential growth, really. And I have some ideas like parallelizing some of the early stages of the calculation to different machines, or using different multiple machines to check the calculation so that you can potentially run the calculation for a longer period of time. Or, yeah, but in the meantime, I have my main job. Like, this was my 20% job, and I got the world record. So I really need to return to my main work as a cloud developer advocate, working on the SRE DevOps practices and provide feedback to the internal product teams. So that's the next year's goal. But yeah, I'd love to try like 300 trillion digits in the near future.
I want to say thank you for the presentation, but also congratulations to you as well.
Thank you.
I wanted to say is, are you going to continue breaking a new record because there's a new, just like what you said about network, the new network coming out is like 5G or 4G implementing in the street. And I thought if you're going to use the same principle as the cloud, would affect the new network that's implementing this today, current generation?
5G mobile?
Yeah, the new network, traffic network is coming out for the new one.
You mean 5G Ethernet or 5G?
Yeah, internet as well.
Internet. So the 5G, like as in 4G, 5G, right?
Yeah.
5G, 4G are for primarily for mobile phones, mobile network, and we have even faster wired network in our data centers and across data centers. So I don't think these like mobile network improvements would affect the these kind of calculations in immediate future. But at the same time, we continue to have improved network. For example, I think we are currently planning no, not we like Google, but like the standard organizations are working on the 400 gigabps Ethernet like specifications or something. So we expect to have like faster and faster network, and these certainly will help.
The reason why I say that is because does it support the Moore's law? The Moore's law, because as the more circuit implement and increase the calculation of what you have achieved, would it continue? It's not gonna tilt down the performance.
There are multiple factors. The easiest and fastest way of doing this kind of calculation is like to install, let's say, 500 terabytes of DRAM on a single machine, but we don't have that kind of architecture yet. Right, so that's the easiest way, and that would probably finish the calculation in a week. And instead, we could use locally attached SSDs instead of using network drives. If we could, for example, if you have a RAID card, that RAID card could support probably 20, 30 drives easily. And if you install 4 or 5 of these kind of RAID cards, you can probably transfer roughly like 50 gigabytes per second or something. So these are much faster than a regular network, and you can probably finish the calculation much, much faster. But yes, there are technical limitations, and there are ideas, and there are limitations on things you can do on cloud, or there are some ideas you can probably do with like specific hardware, but I can't buy hardware, unfortunately.
So last question.
Yes, I'm just curious. So how much of these calculations can be parallelized? Because anybody can think that you need the previous digit to know the next one. And the second question quickly is just, how do you know the digits that you calculate are correct?
Sure, these are good questions. So the algorithm works in a way that you have a long series of summations. Let's see, Chomsky's formula. So you have a long series of summations. So you add up a lot of numbers, and these numbers are very, very big. Like not necessarily 30 trillion digits long, but more than that. And so as these, each of the iteration is kind of independent from each other, you could potentially parallelize some of the early parts. So you can, for example, create a binary tree and add up from the bottom of the tree, and then you will eventually have fewer and fewer nodes and just one node at the top. So that's one of the ideas. And the second question, how did you verify that, right? So there is a separate algorithm called BBP formula or Bella's formula. With this formula, you can actually calculate a arbitrary digits of pi in base 16. So you can, and we did all the calculation in base 16. So you can actually pinpoint and compare some of the last digits in the result. And you cannot convert base 16 to base 10 unless you have the entire result. So you cannot use this formula to calculate pi entirely, not entirely, like from the beginning to the end, but in this manner. So this is just used for the verification. And in order to, and we calculated the last 30, 40 digits of pi in base 16 with this formula on a different machine. And that process took about 70 hours for that 30, 40 digits. And then from after we converted base 16 to base 10, we compared the mods, like modulars of the base, both numbers. And modulars should be the same if these numbers are the same, even if their bases are different. So that's the verification process. I hope that answered the question. Awesome. Thank you.
Thank you.
Thank you very much. Thank you again.
Emma, before you shut your computer down, Emma, just before you shut it down, can we do the wheel of names on your computer?
What's that?
Can we do the wheel of names, the raffle?
So
on your
while
computer?
they set up the wheel of names, a few announcements.
Sure.
One is going to be, again, for maybe not new for those who didn't listen to us previously. So in November, there is Google Cloud Next in London. It's a very cool event. I've been there every year, here and somewhere else. And it's very great. If you're interested in technology, in cloud, do attend. Now, you cannot just go there and register. So if you are interested, you can reach out to us, or Alessandro set up a hot link for that, which is our community manager for UK and Ireland. So you can register to bit.ly/next19UK. Yes. So if you didn't remember it, just reach out to us in our Slack channel, on Twitter, and I'll make sure to set you up with an invite. Remember to specify as a community GDG Cloud London, which is us. So I can
So I guess
you
you also need to remove GDG Cloud.
Yes,
the
please.
GDG London.
Okay, so another small thing is that for November, which is
WT
nowadays
London.
next month, I'm trying to organize an event about Google Stadia. I don't know if you are a fan of video games or streaming technology in the cloud. That might be very cool. So I'm still trying to decide the format. If you have ideas, if you are interested, reach out to me and let's try and sort something together.
Let's try our luck here. Can you spin the wheel?
Sure.
Are you here?
Hi, Sam.
Okay.
Okay, I'll remove your
Thank you.
Okay.
Yeah, next one.
list and spin up again.
Woohoo! So close.
Ouch, Eddie.
Are you here? And the last one?
The last one will be. You could do the same thing with Google Sheet, but this is much nicer, right?
Eddie, he's here.
I think I can remember it. Okay. Is it someone else?
I always give it away though, so I don't mind. If anyone wants it, come and see me or spin it again.
Ooh.
Okay,
Let's
so
spin it again.
you can check. Okay.
Okay, let's spin it again.
No. He's going to do interview after. I usually those, correct? So if you want the license, and maybe I'll even throw one on top of that, go and reach out Eddie and have some interview. Tell him your feedback, your feelings about community, the topics that you're more interested in hearing and interacting with in the future, and we will make it happen.
Cool. It was an honor to have you here in GDG Cloud London for the first time. Hope it's first of many. So if whenever in London, drop by.
Thank you so much.
So before we get to pizzas, if you're comfortable with the photo, can you come and join us for a photo? If you're not forced to, only if you like. Let's take a GDG Cloud London photo. Otherwise, you can go outside and restart the networking time.
Yes, but no pizza yet. So
just after the photo. So
yes.
You might as well just come and take a photo with us.
Yeah, it is. We have like 3,000 people. Okay. So probably we don't know each other. No. Unless we are in a very close team. I actually don't know what team it is. Is he a software engineer? Yeah, software engineer.
Yes, I can totally set them apart. Yes, that and she was the one set up on the sheet. Wait, Antonio! Practicing. You're not joining us? Photo? Just check if... Photo?